This video is all about Coulomb's law. So to start with, what we're going to do is define the concept of charge. Then we're going to talk about the experimental basis of Coulomb's law and how it came to be in the first place. Then we're going to do a theoretical breakdown that extends the ideas of the experimental basis to be a little bit more general. Then we're going to take notice on some notation. And finally, we're going to talk about the superposition principle. So to start with Coulomb's law, let's look at the concept of charge. So we're familiar with the idea of charge. We have positive charge and negative charge, and we know that likes will repel. So in this case, we have two positive charges. These are going to repel each other. And then we could see the same thing if we had two negative charges. These would also repel each other. But opposites are going to attract, and so if we had a positive charge and a negative charge, these would attract one another. Now, what we'd like to do is we'd like to build a more quantitative representation of the same idea. And so we're going to start by having a little bit of a thought experiment. So here what we're going to do is we're going to consider two balls that have some charge. In this case, they're going to be negatively charged, that are hanging from strings from the ceiling. And because these are negatively charged, they're going to repel each other. They have the force from the strings acting on them as well as the force of gravity. And so in this case, like any other when we're talking about forces, we want to start by isolating the body. And so let's just look at one of these charges. Now, for this particular charge, we're going to have our tension acting up and diagonally to the left at some angle of theta relative to the vertical. We have the electrostatic force that is going to be the force of repulsion between the two negative charges pointing to the right and the force of gravity pointing down. Now, because this is going to be in static equilibrium, what we can do is we can sum our forces in the x direction and the y direction. Here we have the sum of forces in the x direction, so this is going to be sum of forces in x is going to be F sub E minus T, the tension, times sine of theta. That's going to be equal to 0 because it's in static equilibrium. We see something very similar for the sum of forces in y. Now, combining these two together, what we end up seeing is we have a relationship between the electrostatic force, the mass of the ball, and the tangent of the angle that we have here. Now, what we could do is we could put on various amounts of charge onto these balls, and then what we could do is we could measure what the angle is very carefully and what the distance is between the two balls by association. And what we would find is this relationship here, where we have the magnitude of the electrostatic force is going to be equal to some constant we're just going to call K for the time being, times the magnitude of the product of the two charges divided by the distance between the two of the charges squared. Now, we want to extend this idea to a more theoretical basis. And so what we're going to do is we're going to introduce vector notation. So here, for the sake of just establishing this, let's consider some positive charge Q1, some positive charge of Q2. The full theoretical equation in vector notation says F vector sub E 1 comma 2, so the force that the electrostatic force that Q1 acts on Q2 is going to be equal to 1 over 4 pi epsilon naught times Q1 times Q2 divided by R squared times R hat 1, 2. And what we're going to do now is we're going to go through and break down the rest of the equation on the right side. So here, the F vector E 1, 2 is the force that charge 1 is going to act on charge 2. We see that because these are positive charges, this is going to act to the right because they're going to repel each other. Q1 and Q2 are the amount of charge. So we're going to go through this in a little bit more detail afterwards. Here, they're both going to be positive. And so you see in this equation, we're not using an absolute value. We're just plugging in the charge, whether it's positive or negative. In this case, they're both positive. Epsilon naught is the permittivity of free space. Ultimately, this has to do with the way that an electric field propagates in a vacuum. And it's, at the end of the semester, going to point to the speed of light. And we'll get to that at the very end. R is going to be the distance between Q1 and Q2. And R hat 1, 2 is the unit vector that points from Q1 to Q2, irrespective of the direction of the force. So this is always going to point from Q1 to Q2. Now, we could also see that via Newton's third law, whatever force Q1 acts on Q2 is going to be equal and opposite to the force that Q2 is going to act on Q1. And so we can see in our diagram here that this force F sub E 2, 1 is going to be equal and opposite to F sub E 1, 2. Now, some notes on the notation and why we want to be careful here. So we have our Coulomb's law in the full theoretical and vector form. And let's consider some various combinations of charge. So we have two positive charges here. We see that the force that Q1 acts on Q2 is going to point to the right. The unit vector that from Q1 to Q2 is also pointing to the right. And this is a result of the fact that when we're evaluating this equation, we're going to be plugging in two positive charges. Now we can consider what would happen in the case of two negative charges. We'd see here on a conceptual level that these should repel each other, which says that the force that Q1 acts on Q2 should be pointing to the right. And again, the unit vector is going to point from Q1 to Q2 by definition. Now, the reason why this ends up working out is because now when we're evaluating this with the two negative signs, we're going to have two negatives that cancel each other. Now, the last case that we can have is a positive charge and a negative charge. We know that these should attract one another. And so this should have some force that Q1 acts on Q2 that's going to point to the left. And again, the unit vector that points from R1 to, that points from Q1 to Q2 is going to be pointing to the right. It's always pointing from Q1 to Q2. Now, the reason why this one is going to point to the left is because you have an odd number of negative signs. So you're evaluating this with a positive sign for Q1 and a negative sign for Q2. Now, this might seem a little bit cumbersome and unnecessary, but I promise that it's actually the easiest way to do this in the end. It just might not seem apparent while we're dealing only with forces. It'll be more important when we're talking about electric fields, electric potentials, and this way of building the formalism is actually the way that we're going to do it when we're talking about magnetic fields as well. Okay, so it's a lot easier sometimes when you're just consistent across the board. So the last thing that we're going to talk about is the superposition principle. Now, consider we have 4 charges here, and we're interested in finding what the force is on Q1. Now, the way that this works is that if we want to find the total force on Q1, what we're going to do is we're going to just add up all of the individual forces that act on Q1 from each of the charges, ignoring that those other charges are there. So let's go through this one really quickly. So we want to find the force that Q2 acts on Q1. We just draw that vector. We add that to our equation. Same thing when we do the force that Q3 acts on Q1 and Q4 acts on Q1. And that's it for Coulomb's law.